So in our last class, we tried to discuss about what's image, classification of image, then how can we convert the analog image into digital image. As we said, image is a series of pixels that are organized in a two-dimensional space. And the pixels are representing the intensity levels. And based on the intensity levels, we can classify images into binary or monochrome image, grayscale image, and the color image. Binary or grayscale image is with two intensity levels, black and white. Grayscale image has 256 intensity levels, and color image with infinite intensity levels. We also classified image into static and animated, especially nowadays. There are different image format, JPG, TIFF, PNG, PNM, GIF. Especially GIF is designed for animating images. The image is one, but that image is animated rather than just making it static. So if you need a static image, you have to save it in either JPG or PNG or PNM or TIFF. But if you need animated, you have to save it in GIF. So according to the file format, we have three types of file format. One, BMP used to save the bitmap image. That means the original image without any compression. But if you need compression, you have to go for either lossless compression or lossy compression. That means we have to go for JPG or JPEG for lossy compression, otherwise TIF, PNG, PNM for lossless compression that are trying to compress but keeping the content as it is. But JPG, JPEG or JPG tries to even decrease the content, the intensities as per the human visualization. We also tried to differentiate between image and the graphics. We said image is a picture recorded from the reality using cameras and the scanners. But graphics is a picture which is drawn artificially using graphic softwares. And their internal content is different. Image is with a series of pixels, but graphics is not with a series of pixels. It's with a series of primitive shapes like dots, like lines, curves, circles, polygons. So based on that, still we can classify. Again, we can also classify based on whether the content is continuous and discrete. So accordingly, there is an analog image or discrete image or digital image. Analog images are images with continuous pixel values, but digital images are images with discrete intensity levels. So digital images are easily recognizable by the computing system, but analogs are not recognizable by the computing system. So accordingly, we can classify our image capturing tools into analog camera and digital camera. The major difference between analog camera and digital camera is in terms of the software, which can convert whatever picture that we have into an image recognizable by the computing system. That means the continuous values are converted into discrete values. Nowadays, image have many application areas. Like we can use it for biometric analysis. We can use it for recognizing different pictures, images. We can use it for traffic monitoring. We can use it for finger verification or identification, face recognition, signature identification, verification. So nowadays it's a hot research area to move from physical world to physicalless world. If you are joining a virtual world, accordingly, everything should be done in a virtual world. So physical appearance may not be required if we are using image recognition techniques. But we have to pass through the challenges. The major challenge, as we said, is memory space requirement, transmission bandwidth requirement, even the complexity of the data management, image data management. It requires a better advanced algorithms for image data capturing, for image data storage and organization, for image data searching and retrieval or use during distribution. Then even the hardware platform needs improvement, because our graphics card nowadays is not recognizing more than 24 colors, but by emitting light, it tries to produce whatever color that we need. So the major concern is to reduce the memory space requirement or to make the image readable by our computing system. We have to start digitizing images. Digitizing image means converting the analog signal into digital signal. Towards that, the bitmap image should be compressed. But during digitization, there are steps that we have to follow before compressing itself. That means we have to first sample out. After sampling, we have to quantize. After quantization, we need to go for compression. Why we need sampling? Sampling is the process of selecting representative pixels from the continuous space available in a two-dimensional image space. So during sampling, the major issue is the sampling rate. Nowadays, the sampling rate is decided based on experimentation, especially which pixel is representing those pixels around that pixel. For that, experimentally, we have to decide, like, can we sample per 4 pixel or can we sample per k pixel? So that means out of the different sampling techniques, the most convenient one for sampling analog images, the systematic sampling. Systematic samplings are trying to capture per k steps, but deciding that k steps as a sampling rate is required. And it's decided based on experimentation. What's used by JPG may not be used by PNG or TIF. So the sampling is the first step that converts the continuous space into discrete space. After converting the continuous space into discrete space, even within that discrete space, every pixels are taking continuous values. That means we have to decide about the bit depth. Our computing system is understanding only zeros and ones. So how much zeros and ones to assign for every pixels? That depends on what kind of image is that image, or what is the intensity level of a given image. In terms of intensity, we divided image into monochrome, grayscale, color. Monochrome images have 2 intensity levels, so they need, in terms of binary, logarithm of 2 to the base 2. That means 1 binary bit is enough. So 0 is assigned for black, 1 is assigned for white. But when you come to grayscale image, there are 256 colors, possible colors. So for those 256 possible colors, we have to have 8 bits for representation of every color that are assigned for a given pixel. So logarithm of 256 to the base 2 will give us 8 bits. So we are using that 8 bits for representing a grayscale color starting from 0 up to 255. Now the challenge is not with monochrome or grayscale. The challenge is with color image, because within a color image, we have infinite colors. Just by mapping or by emitting light, different colors are nowadays generated. So as a result, the color image is modeled using different modeling techniques. One of the known modeling techniques is RGB color model. And most of nowadays, output devices and input devices, including the computer memory, graphics card, the camera, the digital cameras that we are using, scanners, television screens, mobile screens, they are using RGB color model, because RGB color model is an additive color model. That means when they are mixing, they are trying to maximize the number of colors. So given 100% red, 100% green, 100% blue, we will expect white color. But to get that white color, if you are not using additive RGB model, we can't get it. There is a subtractive color modeling which is used basically by printers. Printers are mixing color. They are not emitting light. That means they are subtracting. So they are trying to mix and produce a color opposite of the additive color modeling. 100% red, 100% green, 100% blue colors are producing the origin of the colors white color. But when you go for subtractive, since they are applying AND operator 100, 010, and 001 for red, green, and blue colors, produce as AND all 00s. All 00s means the color is black. So as a result, mostly subtractive color modeling, which are using AND operators, are used in our printers, but otherwise most of the output devices and input devices are using additive RGB color models. As a result, they are emitting light to produce as per our human sense organs. That means how our eyes visualizing using rods and cones. It's trying to produce the required color. So by using minimum number of colors, by emitting light on those colors, there is a possibility to come up with different colors as per the color of the image. So as a result, when we are also quantizing color images, we have to take into account the RGB combinations. We know that whenever two colors are combined, how many possible colors we can produce? Around 256. That means for each color, we can assign logarithm of 256 to the base 2. That means 8. So for color image, for red color 8, for green color 8 bit, for blue color 8 bit, a total of 24 bits are used, which are producing thousands of pixels with their binary representation, which is used for even 2 to the power of 24 will give you more than 16 million colors. That means there is a possibility of representing 16 million colors. That means 16 million intensity levels. So it is almost enough for color that we have nowadays and using in our day-to-day activities. But the problem is, as the number of colors increase, the memory space requirement also increase. As the memory space requirement increase, we are unable to save as much image as possible. So there is a need to control the number of bits that we are assigning for every pixels. That leads us to compression. But see, one of the example we have to understand whether based on an increase in the number of colors, whether the memory space requirement for the image increases or decreases. Given a 1614 by 418 pixel image, if an image is with 1614 pixels column-wise, 418 row-wise, if it is a grayscale image, how much memory space it requires? We have to multiply 1614 by 480, which is giving us around how much pixels? Around, if you multiply with in a grayscale image, 8 bits, will get around 307, 200 bit. That means a grayscale image is requiring 307, 200, 8 bits. So that means the number of pixels available is 307, 200 pixels. If you multiply it with 8 bit, you will get the memory space requirement for a grayscale image. But if it is a color image, we have to multiply with 307, 200 by 24 bits. So as the number of bits increase, the memory space requirement for a given image also increase. But for a monochrome image, since there are only 2 pixels, they are requiring only 1 bit. That means 307, 200 bits. So while grayscale image is requiring 307 kilobytes, a color image is requiring 921 kilobytes. So as the number of colors increase, even if we are using the same number of pixels, the memory space requirement increases. So since we are living in big data society, to solve such kinds of problem, we have to go for compressing the image. Compressing means we have to reduce the number of bits used for representing every pixel. As the number of bits decrease, the memory space requirement for those images also decrease, but we have to also deal with the naturalness and quality of the image. So in behind, we have to compromise, because as the number of colors decrease, the image becomes more of light. That means it is the quality and the naturalness of the image starts decreasing. But we have to start decreasing the quality and naturalness image without making sense for the human eye. So in behind, through compromise, we can go for compressing the image such that we can reduce the number of bits required for representing every pixels in a given image. Sometimes you can also adjust, even if we have 24 bits for a color image, for every red, blue, and green color, there is a chance to give it equal chance, 8 bits. But giving equal chance means both colors are equally applicable. But sometimes maybe some of the colors are more applicable than others. Accordingly, we have to adjust also our color modeling. Like in this problem, the green color and the red color and the green color are more sensitive for human eyes than blue, because mostly the luminance of a given image is dependent on red and the green color as compared to the blue color. So the solution is we have to give more bits for red and the green as compared to blue, so that we can magnify the red and the green color. So what kind of proportion we have to use? If the red and the green colors are more sensitive for human eye as compared to blue by 1.5 times, we have to give for red 1.5, for green 1.5, and for blue 1. So finally we'll get the proportion of For red and the green, 9 bits, and for blue, 6 bits, which is still giving us 24 bits. So the major thing here is since images are requiring more space, one of the challenge we have is memory space requirement. As the number of images increase, memory space also increase. Transmission bandwidth also needs to increase. But as compared to an increase in image data, the memory space and the bandwidths are not equally increasing. So the solution is we have to compress. Compressing means reducing the number of bits used for every pixel. By reducing the number of pixels, bits used for every pixel, we have to make sure that the image is not losing its quality and naturalness. In this two image, the original image is 6 megabyte, but the compressed image is 24 kilobyte, which is saved using JPG. But if you try to see the difference between the two, we can't identify any difference between the two. Both images are looking the same. But if you are using image viewer like GIMP, you can see the difference that's available internally, content-wise, between the two images. While the original image is more of dark, the one which is saved using JPG images, more of light, because it has lost most of the colors internally. Just by emitting light only, it looks like the same as the original image. So image compression is a must, especially for those images that we are uploading over the internet in constructing our websites and the web pages. But if you are using, again, for designing different applications, still compression is required. But what kind of compression we have to use should be a concern at that point. That's why nowadays we have two paradigms in image compression. One is the lossless image compression, the other is the lossy image compression. So the major advantage of image compression is saving memory space and also saving transmission bandwidth. Says that we can keep as much image as possible in our limited memory space, and we can start transmitting as many images as possible with the limited bandwidth that we have. But what kind of algorithm we have to use? Again, the algorithms that we are using, even if compression techniques are optimizing the memory space and the transmission bandwidth, they need an extra processing memory in our in our RAM or in our memory space hard disk, because there is a temporary data which is kept until the compression complete. But that one is dependent on what kind of algorithms that we are running to compress. So still the compression algorithm should be again optimized. Without taking that much extra processing, they have to start compressing and giving us a compressed image, such that we can optimize our memory space, such that we can optimize our transmission bandwidth. So when we are compressing again, there is a trade-off, because by how much we have to compress the image. As we are compressing more the image, we are also saving more memory space. But the problem is, as we are compressing more, we are losing the quality, the naturalness of the image. So the degree of compression should be experimentally decided without affecting that much the quality and the naturalness of the image. We have to decide about the degree of compression that we have to use. in a loosey compression or in a lossless compression. But again, as the degree of compression increases, the compression algorithm is requiring more computational resources, more processor speed, more hard disk memory or random access memory. So during data compression, the trade-off that we have to deal with is how much degree of compression we have to use without affecting the quality and the naturalness for human eye. Says that the distortion is tolerated by the human visual sense organ eye. They have to see the same image, whether it's compressed or not. Plus, tolerating the computational resources that we have. So by dealing with those things, we have to select the best algorithm. So towards that, nowadays there are, as we said, there are two paradigms in image compression: lossless compression, loosey compression. Why lossless compression and the loosey compression? The loosey compression is especially critical for multimedia data. Video, audio, and the image has to go for loosey compression. By losing some of the content, we have to start compressing image, video, and audio without affecting the sense organs of human. Says that they have to see the same image always, they have to hear the same audio always, they have to visualize the same video always. But by applying loosey and by reducing some of the content from multimedia and keeping the quality and the naturalness of the multimedia, will give sense to save more memory space. But again, the loosey one is applicable only for those multimedia, including image, that we are using for constructing web pages, websites, and for using them for something. But otherwise, if you are using image for designing an application, the loosey one is not preferred. Since the content is lost, we are not designing an effective, efficient image processing for some applications, whether it's face recognition or signature recognition or biometric analysis or traffic monitoring. We have to go better for lossless compression. The name itself is lossless. Still, compression is possible without losing the content of the image. So both the lossless and the loosey has their own advantage and a disadvantage. If you see the lossless one, without reducing the content, if we save the compress the image and save it, then after compression there is a model, and if you decompress back, we can recover the original image as it is without any loss. But in the case of loosey compression, again we can go for compression, then if you decompress back, it's not possible to get the original image as it is. Recovering the original image is possible only in the case of lossless. That's why we need also lossless for designing different applications using image processing. But in the case of loosey, even if the image looks like the same, since internally content is lost from the image or audio or video, so we can't use it for designing an application. But as compared to lossless, the loosey one is saving more memory space. So if you want to save as much image data as possible within a given limited memory space, it's better to go for loosey compression techniques. But if you need that data for designing an application, whether face recognition or signature recognition for biometric analysis, or for classifying agricultural products, or for medical imaging, or for optical character recognition or for image retrieval, it's better to go for the lossless one. Since we are not losing the content, but we are saving a space required for keeping the image. But even if we are reducing the content, as we said earlier, we have to make sure that the quality and the naturalness is kept with the lossy data compression itself. Says that the image always looks like the same. So in general, how can we do lossless compression? Mostly without lossless compression are done without affecting the content. Without losing any of the content, an attempt is made to compress and reduce the bit representation for every pixels in an image. Settings can be done by simulating the statistical redundancy observed within the pixels that are available in a given image. Because in any image or in any textual document or in any audio or video, there are statistical redundancy. We are using the same thing again and again. The same colors are used, the same waves are used, the same alphabets are used for producing an image. Words like Mississippi. The best example, Mississippi has around 11 characters. Those 11 characters are produced from 4 distinct characters. So statistical analysis says almost on the average, in any textual image, video, and audio data, we have 15% redundancy. So at least by using lossless, we can go on compressing an image up to 15%. By using lossless, the advantage that we have is, given an original image, after compressing that original image, and then if you decompress back that compressed image, there is a possibility to recover back the original image in the lossless case. So that is a great advantage of lossless compression. But the problem with lossless compression is the compression is not more than 15% on the average. So if you need more compression, it's better to go for lossy one. So in the case of lossy, there is a possibility of reducing even the content. Some of the pixel values are reduced without affecting the visualization of our eye. We have to feel the same image always, even if the content is reduced. That can be simulated based on the visualization of our eyes. Our eye is more sensitive for, not color. Our eye is more sensitive for light, brightness, luminance. So by adjusting the brightness and by reducing as much color as possible, still we are generating the same image with the same quality and naturalness. But since the content is lost, an image with lossy compression is very difficult to use it to design an effective and efficient applications. So the advantage of lossy compression